So we're going to start thinking about aldehydes and ketones as one of the last functional groups that we're exploring as we kind of wrap up our odyssey in terms of looking at the way that various functional groups have specific reactivity. And if you're wondering about why this matters, we're going to think about molecules like vanillin or cinnamaldehyde or 2-methyl-indecanal, which are all examples of molecules that are found really within very common, so things like ice cream and cinnamon and perfume. So just as an idea of where we're going to talk about aldehydes and ketones, that's chapter 12. Then we're going to explore carboxylic acids, that's chapter 13. We're going to wrap up with acid halides, anhydrides, esters, amides, and then enolate anions, that's chapter 14 and chapter 15. So when we think about functional groups of aldehydes, that's a carbonyl group that's bonded to a hydrogen atom. The functional group of a ketone is a carbonyl group that's bonded to 2 carbon atoms. When we think about IUPAC names, the parent chain is going to be the longest chain that contains the carbonyl group. And then for an aldehyde, if we change the suffix from E to AL, so for a ketone, that's the change from E to ONE. And then for an unsaturated aldehyde or ketone, we're going to show the carbon-carbon double bond by changing the infix from AN to EN, and then the location of the suffix is what's going to determine the numbering pattern. So for a cyclic molecule in which the CHO is bonded to the ring, we're going to add the suffix carbaldehyde. And so it's useful, I think, for us to really think about a couple of things. So when we're naming these compounds, we want to be aware of all of the components of naming that we've talked about before. So numbering our carbons to find the longest possible carbon chain, being aware of other functional groups, and then thinking about stereochemistry or orientation in space. So take a moment and see if you can name the 2 aldehydes and the 2 ketones that are shown here. And again, pause if you need to. Check your work. So 3-methylbutanol, 2-propanol, 5-methyl-3-hexanone, and 2-methyl-cyclohexanone. And then it's worthwhile to think about priority. So this isn't something we've talked about yet because we've really only been looking at individual functional groups. But now that we're starting to complete our complement of functional groups, we need to start thinking about what's going to have the greatest priority. And so in this case, when we're thinking about carboxyl groups, they have the highest possible priority, then an aldehyde, then a ketone, then an alcohol, then an amino, and then a sulfhydryl. So for example, if I were to look at this molecule, the alcohol has the greater priority, so it would receive the 1 or the lowest possible numbering. In this compound, if I'm looking at the priority between a ketone and an alcohol, the ketone should get the lowest overall numbering because it has the higher priority than the alcohol. It's also useful to recognize that there are common names for aldehydes and ketones, so formaldehyde, formic acid, acetaldehyde, and acetic acid. And the same thing is true for ketones. So when we're thinking about these ketone names, we're always going to have the lower molecular weight group in the first part of the name. So if you think about that for these 2 molecules, how would you name these 2? And then what really matters for us is we're starting to think about how structure determines function. And so we're looking at aldehydes and ketones as polar compounds that interact through dipole-dipole interaction. So the carbon has a partial positive charge, the oxygen has a partial negative charge. And that means that these are going to be compounds that have higher boiling points and are going to be more soluble in water than nonpolar compounds of a comparable molecular weight. So if you take a look at this table, there's some data that you should be able to walk away with. So notice these all have similar molecular weights, but their boiling point is vastly different. And that's because alcohols and carboxylic acids are compounds in which hydrogen bonding between molecules is possible, whereas for alkanes or ethers, that's not as feasible. And the reason for that is alkanes don't participate in hydrogen bonding at all. Ethers are only receive hydrogen bonding. They cannot donate hydrogen bonds. But alcohols, aldehydes, ketones are examples of molecules that can participate in some additional hydrogen bonding. Obviously, propanoic acid would be a great example where you have both the carbonyl group with the oxygen that can receive a hydrogen bond, as well as the hydroxyl group that can both receive and donate a hydrogen. So the most common reaction theme of carbonyl groups is the reaction of an electrophile and a nucleophile to form some type of new covalent bond. So that's a tetrahedral carbonyl addition where I take my carbonyl group, I add my nucleophile in, and now I have a tetrahedral intermediate. That's important because we're going to look at a class of reactions called Grignards. So Grignard reagents are prepared by adding an alkyl or aryl halide to a suspension of magnesium metal and diethyl ether. And what's really interesting about this is that once I form this Grignard reagent, it's actually the insertion of the magnesium between the carbon bond and halogen. Now these Grignard reagents are going to behave as carbanions. A carbanion is an anion in which the carbon has an unshared pair of electrons and carries a negative charge. So a carbanion is a good nucleophile, and it's going to add readily to the carbonyl group of aldehydes and ketones. So these are two different representations of a Grignard reagent. Both are correct. I find that this representation is the most useful because it shows the lone pair of electrons and the negative charge, which is the signal that it's going to behave either as a nucleophile or a base. Now, Grignard reagents are going to react strongly with anything that is a proton source, so protic acids, for example. Given what you know about balancing equilibrium reactions, take these pKs into account and tell me what's the conjugate acid, conjugate base, what's the stronger acid, stronger base, and what's the direction of equilibrium. And if you need to, go ahead and take a pause to be able to answer this question. While you're doing so, take into account the fact that anything that is a proton source is going to react with a Grignard reagent. Some examples are shown below. Hopefully you were able to remember that the lower the pKa, the stronger the acid. And so in this case, water is our stronger acid. And our Grignard reagent is going to be our stronger base. It's going to react with water to take that proton, form an alkane, and generate the hydroxide ion. Now, isn't it interesting? We know that hydroxides are strong bases, but in this case, they are actually weaker bases than the Grignard reagent itself. That's how strongly these react. So here's another example, including the mechanism. So it's important to think about how these molecules react in terms of the direction or the movement of electrons. You should also be able to identify the conjugate acid, conjugate base, stronger acid, stronger base. When we think about the way then that Grignard reagents react with aldehydes, they're going to provide a primary alcohol. So Grignard reagent is going to be the nucleophile, which attacks the electrophile, in this case formaldehyde. That's going to generate a magnesium alkoxide, and that magnesium alkoxide is going to take a proton from hydronium to generate one propanol. And again, if we think about this, the reaction with any aldehyde other than formaldehyde is going to give a secondary alcohol. That's an important distinction to make. So here's an example of a reaction of a Grignard reagent with an aldehyde that gives a secondary alcohol. So this is acetaldehyde. Here's magnesium alkoxide that's formed. Notice the oxygen takes a hydrogen from hydronium to generate this secondary alcohol, in this case 1-cyclohexylethanol. The reaction with a ketone is going to give a tertiary alcohol. So if in this case my Grignard reagent adds into acetone, I'm going to generate a tertiary alcohol where my oxygen again takes the proton from hydronium, generating 2-phenyl-2-propanol. Now, if I think about this in terms of other possible reactions, I also need to take into account reducing agents. So what's shown here are the reducing agents: sodium borohydride, lithium aluminum hydride, and DIBAH. These are all examples of reducing agents that can generate a hydride, which is unique. This is a hydrogen that actually carries the electrons with it and functions as a nucleophile. So as shown in the mechanism here, these hydrides attack as the nucleophile and electrophile, and then if there's a protic acid that's available, the O- that's generated is going to take that proton and form an alcohol. When we think about the reactivity then of reducing agents like sodium borohydride, it's important to consider their selectivity. So sodium borohydride is relatively mild, and the reactions typically run in water, methanol, or ethanol solvents. So 1 mole of sodium borohydride can reduce 4 moles of ketone or aldehyde. These carboxylic acid derivatives or alkene double bonds are not going to be affected. So there's only some of this molecule that's actually going to be reduced. And that's what's shown here. So I reduced my aldehyde, I reduced my ketone, but my ester stays intact. So lithium aluminum hydride is very different. Lithium aluminum hydride will not affect alkene double bonds, but it will reduce carboxylic acids and esters down to primary alcohols. It will reduce amides to amines, nitriles to primary amines, and can even be used to open epoxides to form alcohols. The last mechanism we're going to take a look at today is the mechanism of oxidation. So we've talked about Grignard reactions, we've talked about a reduction, now we're going to talk about an oxidation. And the oxidation here is a chromium oxidation where the alcohol is going to function as the nucleophile to attack chromium. We're going to add a proton, and then water is going to function, in this case as a base, to take a proton, and the electrons from that bond are going to come down onto the oxygen. And then if we have a base, we could also take a proton away to also generate electrons onto that oxygen. And that's what generates our aldehyde or ketone. So this mechanism of oxidation is relatively generic. And for now, that's all that you'll need to know in terms of mechanisms of oxidation. So let's take a moment and look at a couple of examples. So here are 3 Grignard reactions. Can you predict the products? Again, take a moment, pause if you need to draw out the mechanism, and then check your work. So in this case, you should have seen the formation of alcohols. Grignard reactions with ketones are always going to generate alcohols. In this case, we're generating tertiary alcohols. Now let's take a look. Can you predict the reaction products or reactants based on the conditions shown? And again, take some time if you need to. You can always check your work later. Notice here, right, the starting material for a sodium borohydride reaction is always going to be a ketone or potentially an aldehyde. And then if we're going to oxidize, we're going to think about starting with alcohols and then oxidizing selectively to a ketone if we use PCC, or all the way up to a carboxylic acid if we have a primary alcohol. The next thing we're going to talk about after we finished our conversation about aldehydes and ketones is going to be enols. And we'll get back to that shortly. We've got a little bit more to do on aldehydes and ketones. Again, thanks for your time.